All right. Welcome to our lesson on radicals and simplifying square roots. So I'm going to give you a lesson on this because we're going to use it in chapter 8. And this is going to go into your participation, notebook grade, that kind of a thing. So you're going to have to do two things. You listen to the lesson. I'm going to ask you two questions throughout the lesson. I'm going to answer them and tell you the answers. And that will be question 1 and 2 on your assignment. And then I'm going to ask you to simplify 8 additional problems. Okay, so there'll be 10 questions that you guys will do in order to fulfill your requirement for this assignment. And this will be your second assignment in that category. All right. We're going to talk about radicals. We would normally talk about simplifying radicals, but we're going to limit it to square roots because that's what we're going to use in chapter 8. But let's talk a little bit about terminology. I've written this symbol right here. This is an A, and that's an N, okay? And there's 3 parts to it, okay? The little N right there is called the index, all right? And if you don't see an index there, it's understood that it's a 2, and it's understood that it's a square root, and that's what we're going to be dealing with. This symbol right here, this one right here, this symbol, many of us mistakenly call it a square root symbol. It's only a square root symbol when the index is a 2. And again, you won't see it because it's understood. But it's a radical symbol. That's what we call that because it could be a cube root or a fourth root. All right. And the other term that you definitely need to know is this guy right here. The number underneath the radical is called the radicand. So I put the 3 definitions over there. The index is N, the radical is that symbol, and the radicand is the number or the A that's underneath it. So if we have something that looks like this guy right here, all right, we would say that's the square root of 16. The reason is because we don't see the index. There actually is a little 2 written in there, but we don't write it. Remember, if we wanted to write 3 plus 2 equals 5, like this, we could write 3 over 1 plus 2 over 1 equals 5 over 1. But what a pain in the neck, okay? So we don't write the ones. We don't write the denominators, but they're understood. Again, we use square roots more than any other root. So we don't write the little index in there, but it is there. All right. So the square root of 16, if we forget, equals 4, and that's because 4 times 4 equals 16. So we have 2 of the identical numbers, okay, that multiplied together give us 16. We could also write that. I hope most of us know that we can write that as the same thing as 4 squared equals 16. Okay. Notice that the 2 matches the 2 index. So that's why it just goes away and we get 4. All right, we could have something that looks like this, and we're not going to do these. We normally do these in a normal year, but we're going to just concentrate on what we're going to use for the remainder of the year. We wouldn't call that the square root of 16. We would call that the cube root of 16 as the index is 3. That would be a cube root. So we'd be looking for 3 numbers that when they multiply together, they give you 16, which there is none. It would be an irrational number. Okay, so right off the bat, here's our question number 1. The first question you need to answer, what do we call this symbol, that square root? Your answer is a radical. Okay, we call it a radical. So the answer number 1, when you have a notebook piece of paper that you're going to do the simplifying the radicals, you're going to put number 1 on it. Okay, so you could even take out a piece of paper now and put number 1 on it and just answer it radical. All right. There'll be one more of those questions along the way, and then there'll be 8 simplifying that you'll do at the end. All right. So what does it mean to simplify a square root? A square root is said to be simplified if there are no perfect square factors in the radicand. So here comes that terminology. The radicand, the number underneath the the radical, is not a fraction. It cannot be a fraction. And the third thing is the radical is not a denominator. So we kind of messed that up a little bit. We'll clean that up right here. We'll go kind of clean that up. So it says the radical, okay, is the radical is not in the denominator. Okay, so we can't have it. We don't care about if it's in the numerator. That's okay. And that will happen in Algebra 2. You'll have to actually rationalize the denominator, but we'll talk a little bit about that today. Okay, and there's actually a fourth one. The radicand cannot be negative, and we'll get into that a little bit. The last section we do before the end of the year. Okay, but for right now, we're going to just kind of skip that one. All right, so we need to talk about, if we're talking about number one, there's no perfect square factors in the radicand, then what are we talking about when we say perfect square factors? Okay, we're talking about factoring that radicand, and you guys have been doing a great job factoring. So factors that are a product of two identical numbers. So hopefully you can see that I gave you the first few perfect squares. Hopefully you can see that that's 2 squared, and 9 is 3 squared, and 16 is 4 squared, and 25 is 5 squared, and so on and so forth. Okay, so you can never have a radicand where one of its factors is 4, 9, 16, 25, etc., etc. It would not be considered simplified. Okay, well, we do have some properties for radicals, and we're going to use these in order to simplify them. So we're going to use the number one. We're going to talk a little bit of, we're going to use that concept. And then we're also going to use these two properties. There's a few more, but these are the two that we're going to get to. And the first one is the multiplication property. It says that the square root of A times the square root of B equals the square root of AB. Okay, so that's like the square root of 2 times the square root of 8. Now take a look at that. 2 doesn't have a perfect square, and neither does 8, but we can say that that's the same thing as 2 times 8, which is the square root of 16, which now we can take the square root. The square root of 16 is 4. All right? And we have the division property, basically meaning we can either split the numerator and the denominator up, or we can put the whole fraction underneath one radical symbol. And you're going to use it both ways. So we need to know this both ways. So we have the square root of A divided by the square root of B is the same thing as the square root of A divided by B. So we might have the square root of 3. Let's do it the other way first. Okay, so we might have the square root of 12 divided by the square root of 3. Again, we can't evenly take the 12 and 3 are not perfect squares, but we can say that that's the same thing as the square root of 12 divided by 3, which is the square root of 4, which is 2. So that certainly helped us simplify it. But we might want to use it in reverse. The square root of 3, let's go in the reverse. Let's have Mr. Darenthal figure this out, okay? The square root of 3 divided by 4. Now, we can't, 3 divided by 4 is going to give us 0.75, and that's not going to be a perfect square either. But remember, we can't have, it's not simplified if the radicand is a fraction or there's a radical in the denominator. So we could split this up, square root of 3 divided by the square root of 4. And now we could take the square root of 4, which is 2. And this would be considered simplified. Why? Because the new radicand now is 3. It's just the number underneath the radical. And there's no perfect factors in that radical of that radicand of 3. The radicand 3 is not a fraction, and there is no radical in the denominator. The denominator now has been rationalized to the number 2. All right? Well, let's talk a little bit before we get to examples. All right. I think I kind of messed these things up right here. I don't think we have to have that in there. But we talked about perfect square factors up here, 4, 9, 16. What happens if we have variables? Well, you guys know the laws of exponents, and you know that if we have x times x, we get x squared because we add the exponents. Okay? And x squared times x squared is x to the fourth. All right? And x to the third times x to the third would be 3 plus 3, which is 6. So if I wanted to take the square root of x to the sixth, that would be the same thing as x cubed. Why? Because x cubed times x cubed is x to the sixth. Just like the square root of 16 is 4, because 4 times 4 is 16. All right? Notice that our perfect squares, when it comes to variables, they have to have even exponents. If they have odds, they're not going to be perfect squares. And we'll talk about that in a bit. All right? So we're going to keep in mind this perfect square concept and this list of 3 things. Okay? We have to answer, does the radicand have any perfect square factors? We need to answer no. Is the radicand a fraction? We need to answer no. Is there a radical in the denominator? We need to answer no. We need to answer no, 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 and then we know it's simplified. If the answer is yes to any of those questions, then we've got some work to do. All right? So when we simplify square roots, there's 2 methods. The first method is just search for perfect square factors and use one of the properties to help us simplify it. Or method 2 is to use prime factorization. Now, some students like to use a combination of these. They like to use method 1 when it's just a very simple square, like the first one, square root of 20. But they'll use method 2 when we get down to where we have some of these variables underneath the radical. Okay? So I'll do them all in both methods. So if I want to simplify the square root of 20, method 1 would be to factor 20. To factor 20 into 1 times 20, 2 times 10, and 4 times 5. So I've factored 20, okay? And now I look at that list of factors and I say, are any of those perfect squares? And sure enough, 4 is a perfect square. So I'm going to use my multiplication, and I'm going to say that square root of 20 equals the square root of 4 times 5. And I can break that up into the square root of 4 times the square root of 5. And I can actually take the square root of 4 because it's a perfect square of 2 times the square root of 5. And now it's simplified. Why? Because my new radicand 5, I ask myself, are there any perfect square factors of 5? The answer is no. Is 5 a fraction? No. Is there a radical in the denominator? No. So no, no, no means I'm done. Well, method 2 would be use prime factorization, which we did in 7-1. We would factor 20 into its primes, 10 times 2, 5 times 2. And we would write the prime factorization underneath the radical, 2 times 2 times 5. And this helps us when it's not a square root, when it's cubed root or fourth root or fifth root. So it's kind of a good method. Since it's a square root and our index is 2, we're looking for pairs. For every pair we can take, here's a pair of 2s, we can take 1 out and cross off the pair. And now we just neaten it up. It's always multiplication. Whenever you bring something out from underneath the radical, it's multiplication. So we would have 2 times the square root of, and the 5's got to stay underneath the radical. And we get the same answer. All right? So let's do number 2, the square root of 32. We could do it in method 1. I'm going to speed this up a little bit. Method 1, we could factor it out. Or some of you will see right away that the square root of 32 is the same thing as 16 times 2, okay? So we're kind of using this property right here, but we're going backwards. Okay, we're going to go this way with it. 8, all right? And so I could break that up because 16 is a perfect square factor. That's why I factored it out. 16 times the square root of 2. And we know the square root of 16 is 4 times the square root of 2. And now that's considered simplified. Okay. Why wasn't the square root of 32 considered simplified? Because it had a perfect square factor of 16 in it. Okay. Hopefully some of you might see that it also has a perfect square factor of 4. 4 times 8. But then 8 would also have a perfect square factor of 4. So you try to get the largest. When you factor it out, you want the largest perfect square factor. And if you don't quite see that, you can always go back to this factor tree. 16 times 2, 8 times 2, 4 times 2. You got to get it to its primes. You have to get it to its primes. And we're going to go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And if we multiply 2 times 2, we get 4. Times 2 is 8. Times 2 is 16. Times 2 is 32. Again, because it's a square root, so the index is 2. For every pair, I'm going to take 1 out and cross off the pair. There's another pair of 2, so I can bring it out. It's always multiplication when you bring it out. And now I just need to clean it up. On the outside, we have 2 times 2, which is 4. And underneath the radical that's left over is a 2. So we get 4 root 2. All right? So hopefully that helps. Take a look at number 3. Now we're going to introduce the variable. And a lot of times students like to use the prime factorization when they get into the variables. So we could say that this guy is the square root of 4 times 5 times x times x. So that would be, again, we could then break up the square root of 4, or the 4 into 2 times 2 times 5 times x. For every pair, we're going to take 1 out, cross off the pair. Pair of x's, we're going to take 1 out, cross off the pair. And we're going to neaten it up. 2x on the outside is always multiplication, and the 5 stays under. Okay? Some of you might just say, well, I know the square root, I know that that's 4 times 5, so that's 2 root 5, and the square root of x squared is x, and that's fine. You can do that. Let's try number 4, 27. Some of you can see that it's 9 times 3, and the square root of 9 is 3. But oftentimes, students like to use, when they start to get this, 9 times 3, 3 times 3, they'd like to use prime factorization. So if we do that, we're going to get 3 times 3 times 3, x times x times x, y times y. That's completely prime factored out. Okay? We call that writing it in expanded form. So here's a pair of 3s, and we get to pull 1 out. There's a pair. Got to do this fairly neatly, and those of you that have me know that Mr. D is not the neatest guy. So we'll cross that out. And there's a pair of y's, because you have to see what's left underneath the radical. So we have to neaten this up. So that would be 3xy times the square root, and what's left over? 3 and an x. 3x. Okay, so when they don't have a pair, they just stay underneath the radical. Some of you can look and say, well, the square root of 27 is 9 times 3 is 3 times 3. Okay, x cubed is the perfect square factor is x squared times x, and that'd be x, and so on and so forth. You can speed this up as you see it. Okay. 2 more examples. Let's take a look at this. Okay, so why is number 5? Number 5 is not simplified because we have a radical in the denominator. So the first thing we want to try to do, we can't have that radical 2 or that square root of 2. So what we can do is use our law of division. It's the square root of 32 divided by the square root of 2, or we can say that's the same thing as the square root of 32 divided by 2, which gives us the square root of 16, which is 4. Okay? That's kind of nice. Worked out nice and neat for us. But take a look at number 6. Number 6, shoot. If I say the square root of 3 over the square root of 25, if I try to do 3 divided by 25, that doesn't work for me. It won't neaten it up. And why is it not simplified? Because the radicand right now is a fraction. But again, we can use our law and we can say, well, the square root of 3 divided by 25 is the same thing as the square root of 3 divided by the square root of 25. Excuse me. In this case, we can't take the square root of 3, so we leave it as the square root of 3, but we can take the square root of 25, which is 5. And now that is considered simplified. How do I know that? Because my new radicand, the radicand here, is now 3. And so I have to ask myself those 3 questions. Are there any perfect square factors in 3? No. Is 3 a fraction? No. Is there a radical in the denominator? No. Our denominator is 5. We don't care if there's a radical in the numerator. So here's your answer to the second question. Your second question you need to answer in your assignment is, what was the answer to example number 6? And your answer is the square root of 3 over 5. So when you start your assignment here in a second, you should say your assignment's going to be simplifying radicals. That's how you can label it. And your answer to number 1 is going to be radical. Your answer to number 2 is going to be the square root of 3 over 5. And then I'm going to give you 3, 4, 5, 6, 7, 8, 9, 10. So you're going to have 8 more problems to simplify. Simplify the square root of 72, 98. I'm sorry, I went the wrong way. 72, 125x squared, 98, 150x to the 5th, and so on and so forth. All right? You'll turn that into your assignment. That is the video lesson on radicals, simplifying radicals. All right? Good luck with that, and we'll go over it next time you're in class. Next time you're in class not taking the quiz. We'll see you in class.